Maybe so. Maybe so. Still nobody's liking them. Never get a goddamn thumb up. Not a one thumb up. You're watching this. Thumb up it. Hi, good morning. So, which problem, Cormac? I'm sorry, sir.
It was the second one. I think it's like prove the square root of 2 plus the square root of 2 is irrational.
Oh, did I sign that problem? Yeah. Well, so can you give me the number really quick? 2-3, thank you. Oh, yeah. Oh, that one. Oh, okay, got it. Is irrational. I thought you said irrational, and I was thinking about something else that I'm assigning next. It's like I thought I assigned that already. So it's this one. Show that this is not is irrational, right? Yeah. So tell me a little bit about what you tried to do and where it went wrong.
I just assumed that it is rational, so there is integers a over b that equal it, and then I tried to algebra my way out of it. And
So the way to do this one is with the rational roots theorem.
yeah, I think that I haven't tried it since we did that in class,
Okay,
but I was going to see what you had to say about it first.
do it that way.
Okay.
Is what I have to say about it. Yeah, like honestly, because the A over B, you won't be able to do it with the contradiction method. At least you not the way that I did the first proof. It definitely has to be done with that rational root. So you're going to say x is this. You're going to construct some polynomial. Probably will be a 4th degree thing. C equals 0, and then you'll construct this for which this is a root, and then you'll write out all possible rational roots using the rational zeros theorem, and they're all going to be factors, plus or minus factors of the c over the factors of the leading coefficient, and you're going to see that that's not in that list, so it can't be rational. Because this is, and it's really important to that argument, and you'll get a chance to fix it up, of course, but you really need to say that all possible rational roots have this form, or must be in this list. X isn't in the list. This is kind of make it better than this. Therefore, that's the therefore symbol. X is irrational. That's the flow you want to do. It's so much, honestly, it's like 1,000 times easier.
Yeah.
Yes.
See where we did it again.
Okay.
It's like the same thing now.
Cool. So that's 2, 3, whatever. Yeah, 2, 3. Any other questions on that assignment? No? Cool. So if you could get that to me, I don't know when I said, but like ideally before I go to teach on Friday, and I leave my office at 2, so try to get it there by just tell yourself noon. Just tell yourself noon, get it there by noon, you'll be done with it, go enjoy Friday. And then remember, if something's not great on it, you get to redo it up to 2 times until you get it up to my standards. Yeah, cool, low stress, lots of chance to succeed. Awesome. Before I forget, let me give you the assignment. I'm gonna try to do an assignment every Friday. So in some ways, getting stuff done right the first time helps, because then otherwise things start building up. But this will be homework to do next Friday. I should start putting these on World Class, and I will do that today so that you have them there. 4.1, and this counts as one problem. There's all these parts. And we'll talk about how to do this today. This is where real analysis actually starts today. Very excited, and that's in R and an S and a V. It looks like a lot, but each one's like a tiny little thing that you have to do something fairly simple for, but thinking through each of these examples is going to be really good for your brain. There's one, I got more coming. So just hold on. Also, so that's 4-1. I also want you to do 4-7A, 4-1-2, and 4-1-6. Now I'm done. Also, again, when you're doing your write-ups, include the problem statement. Because otherwise I'll send it back to you. That'll be like a, no, or it might be that. Just like, great, except I have no idea what you're doing. Sound good? Cool. Give that, so we'll shoot for next Friday, ideally. Cool. Well, if there's no other questions, also, if you need to meet with me tomorrow, shoot me an email. We'll set up a Zoom. I'm not going to be in, but I'm available by Zoom, and we can make that happen whenever. So, all right. Yeah. Let's start talking about upper and lower bounds and having all sorts of analytic goodness. This is chapter 4. I guess we're starting here, section 4, chapter 1, something like that, section 4. The title of this section is The Completeness of the Reals. So, this is section 4. Is the lighting okay for y'all? Is the board visible? No glare? Nothing weird? Okay. Section 4, the completeness. And we probably won't get to that until this part, until Monday. And probably what'll happen on Monday is I'll like say the next assignment isn't due till the next Monday, but I'm already seeing that coming. Let's stick with the Friday, tell ourselves that, and see what we can do. You've seen this show before. You know how it goes. All right, let's get a couple of definitions out here. And just a really quick, loose way is, this is the real number line has no holes. No holes in the real number line. That's the loose way to put it. But we need a deeper understanding of that. That's a little bit too loose for what we're gonna do. And it certainly can't prove shit with that. So we got some definitions. I've got a subset of the reals, S. And it is not an empty subset. So there's something in there. There's at least one real number in that set. So we're gonna start kind of gently here. If there is an element X, let's call it M, capital M, in that set. If there's something in that set that's bigger than every other thing in that set, so that M is, I'm going to write it like this because bigger's to the right, and I don't want that to be confusing. So that X is less than or equal to M for all X in the set S. Okay, I'm going to write that out. That's a lot of notation. Take a look at it. Process the notation. Can you make that into a sentence in your head? Let's do some examples. Oh, I haven't, how about what it is? Then, M is the maximum of S. So that's what I'm trying to define. I guess that was kind of rough because it was just a bit dangling. And we write M equals max of set S. It's the biggest thing in the set. That's all. Nothing fancy here. Before we even go on, I would give you a chance. Can you write the definition of minimum? What's the definition of the minimum? Let's write that out and practice using that notation. So let's say little m is the minimum of set S if what? Maybe somebody can help us with that. Yes. Can I see the language you used to do that?
Yeah, so you said so that
was just like copy.
Oh, this is just, you haven't written it yet. Okay, got it. Yes, that's essentially, can someone tell me, what is the statement? M is the minimum of set S if,
X is greater than or equal.
okay, so,
Or to, yes, little m. For all x.
there we go. Yeah, yep. Cool, awesome. Pretty straightforward. You know this, you can picture this. Let's just make sure, and then let's complicate it just a little bit, because this is where real analysis, like I said, it kicks in. We're not quite there yet. This is just like understanding biggest and smallest, right? This isn't terribly deep yet. So let's just do some examples. Find max S, min S, and let me give you a couple sets. First one, E pi 1 over E 1 over pi. So we'll call that S. Do that one, and then what if S is equal to this set? That's the set of all n integers n. And one more, two more actually. And one more. Sorry, I'll get out of your way here, Christian. I'm probably making it hard for you to see. Okay, thank you. Great. Even chiller. That is an interval. Right there. Is that interval notation cool with everybody? Awesome. So let's just take a minute and find max and min in each of these sets. If you're watching, if you're one of the however many people are watching this, pause the video, play along. Or race the people in this class. Maybe that's what you're doing.
there a notation for like approaching a number?
Not yet. Soon, in 10 minutes, tops. So you see, you're starting to see an issue, right? Yeah. Okay. I'll save that one for you. You get to help with that one. That's awesome. Give everybody a chance. Camila, are you feeling okay on that first one?
I think so.
Cool. What'd you get, friend?
I for the max, and then 1 over e.
Do we agree? You don't agree. Why is that?
I said 1 over pi was,
And why is that?
well, like e is like 2.7, right? Something? And then pi is 3.14, and like 1/2 is bigger than 1/3.
You get, yeah, cool. So I tried to be a little tricky. It's good. It's good. It was meant to be a little tricky. So yeah, we want this one's the denominator's bigger than this one, so it's a smaller fraction. Cool. So there's our min. Pi and 1 over pi. E didn't get to do anything. Dang it. How disappointing. Cecil, you got something for this one for us?
Wouldn't it just be max 17,
Okay, and then what's the min?
-3?
-3. Do we agree here? Camila, you are not agreeing. You get to, now the tables have turned.
I put a max of 16
Why is that?
because it's not less than or equal to 17.
Got snagged here, Cecil, because you can't get to 17, right? So the one right before that is 16, yes. Well, I will give you a chance for vindication later, Cecil. Everybody gets to turn the tables once the tables have been turned. So does everybody see what's up? This is actually a set of discrete numbers. This is -3, -2, -1, 0, on up to 15, 16. Tricky. Christian, what you got here?
I said a minimum of 0 and a maximum of 1, but yeah, the other way around.
Thanks. Yep. I don't know why I did that too. Even when I was writing that, I was like, that feels weird. And now I snagged myself, so I have to be vindicated later. Thank you. Yeah, and they're both rational, so all good. Yeah? Everybody cool with that? Cormac, what's the minimum of this set?
1.
Yeah, so it's this. Let me draw it out. It's on the number line, and I use that open circle to show the closed circles inclusion, open circles exclusion. So the minimum is 1. What's the max?
It would be as close as you can get to 2.
How close is that?
You can always get closer to 2.
You can always get a little closer. So this one's tricky. 2's not in this set, right? And so you say, well, okay, hold on. The max is 1.999, and I'll just write that out. I'm tired. How do I get closer to 2?
Tack on
What if I wrote this? In other words, 1.9 repeating. Is that close to 2? That seems like it'd be really hella close to 2. What is that number? Let's find out. Let's do the repeating number game. Yeah, got the trick. So let's let x equal 1.999 forevermore. I just have to multiply by 10 to get the repeating parts to line up. So 10x equals 19.9. Yeah, good. subtract, got 9x equals, what do I get on the right? I'm just waiting for somebody to tell me. 18. Yeah, 18, cool, thanks. All this stuff cancels, everybody's seeing that? That all cancels. You might have been a little scared to say it, but it's good. So what's x?
2.
So here's a fact that a lot of people aren't aware of, even my math major, my brilliant math major friends. Real number, the decimal expansions are not unique. There are multiple ways to write every real number. So you want me to write 1? That's actually, that'll work too. You want me to write a half? Done. So in a way, it feels like we're approaching, but it's not, it's actually just there. So just keep that in mind, because that's weird, that decimal expansions of real numbers are not unique. Very little known fact. Starting to hint at how strange this stuff is, especially when we start notating with that decimal notation. So Cormac, so Cormac's answer was, there is no max in this set, and that is right. So the max does not exist. Anything you tell me is the max, as close as you try to get to 2, you say that's the max, I'll just pull something a little bit to the right of it. And you can't get to 2 itself. So sometimes a maximum or a minimum. Can somebody give me an example of a set S that has no minimum and no maximum? What you got, Cormac?
If you do the same one but take away the closed brace.
Yeah. This has no max or min. It's got that same problem on the left side here. So here's 1, here's 2. I can't get to either one of those. And as soon as I start trying to make a claim that, oh gosh, everything's gotta be less than that, I'll just tack it up, push another 0 in there. You tell me what you think the minimum is, I'll just move to the left and say, nope, I found one lower. So there's no max, no min for this set.
If you were to, for that original
Yeah.
question, if you were to do something like 1 plus infinity minus 1 over infinity, would that also be like the same?
So can you, for which one are we looking at? This guy?
Yeah, to like try and approach 2.
Are you saying that?
Or with like an infinity minus 1 on top of the other infinity.
You mean like that?
Yeah, but then also have it like, so it'd be like 1 plus that fraction, so you would get like close to 2? Would that just be like the same?
Plus a 1 plus that?
Yeah. Would that be like just the same as like that decimal expansion?
So, this is a great question. I love that your brain is already headed to infinity. Pull it back from infinity. So this is in general a troublesome thing to do computation with. Think of infinity as a place you can aspire to. Much like 2 here, I can aspire to it, but I cannot reach it. So infinity is a place. You tell me, give me a number that feels like infinity, and you say, I say, oh, Google, 1 with 100 zeros, and then you're just like, yeah, I win. So there's no end to that list. Is that suffice? Okay, cool. And we can end up with lots of really scary things if we start tossing infinity in. So, for example, Christian, like infinity times 1, I guess that's infinity. seems like a big ass thing, the biggest ass thing in the world times 1, it's just itself. What's twice the biggest ass thing? Well, seems like it'd be that. And then I cancel, so these two things must be equal, so you cancel, and then you got troubles. Don't use infinity as a number. I guess that's it. I think you got it before, and now I just keep beating you over the head with it, so I'm sorry. But I love that you're thinking like that. I love that you're thinking like that. But what you're inevitably just thinking about is approaching. I think that's really, you're thinking approach with something smaller on top than there is on the bottom.
Yeah.
So now, let's take a look. Let's actually follow that idea up. What if I said this? Now, this thing for n equals 1, 2, 3 is going to get closer and closer to n. And I could say this, if I'm thinking back to calculus, this does equal 2 in the limit. But all a limit is saying, it's an aspirationally, especially limits at infinity, that you tell me how close you want to get to 2, I'll just make n big enough to accomplish your request. So a limit still, it's like a verb still in some ways, not a noun. Yeah?
Yep.
Okay, cool, awesome. So even after I said I would stop beating you over the head. We just had, it was such a good question though. So good. So let's talk about how we can get at this. Oh, I got one more for you. Since we're warmed up, how about this one? Here's one last set, S, and it is the set of all rationals that are bigger than or equal to 0 and less than or equal to the square root of 2. I could write this in another way. It's this closed interval intersected with the rationals. Same set, written 2 ways. The only thing in that set is rational numbers. Find the min, find the max. Somebody got min for me.
0.
Nice. 0. Then since we're chatting, it's good to go for that low-hanging fruit. When Dr. Pat and I puts up sign-up sheets for stuff we have to do, I make sure I get in there right away. So I get to pick the one I want to do. The one I want to do, don't want to do the least. What is the maximum?
Well, like, I always say it's the closest rational to root 2.
Ooh, I love that. That's okay, cool. But then that starts to hurt,
Yeah.
right? Yeah, that's good. You got the idea. So you might say what? So let's start getting. So square root of 2 is 1.41. Somebody got a calculator on the phone. I can't remember. I think a 2's next. Somebody just give me a square root of 2. I'm getting ready to make up.
4, 1, 4, 2, 1, 3.
And then etc., right? And so we know that that's irrational. We've proved that a couple of ways. We know that this is an irrational number, and so this can't repeat, right? This can't repeat, because if it did, it would be rational. We know that repeating decimals are rationals. So let's think about getting close to the square root of 2, but only using rationals. So here's a list of things getting close to 2. Here's 1.4 square root. So I'm just going to grab the first 2 digits. A little bit closer would be, so right, this is 14/10. This is 141/100. It's getting a little closer. So now I'm moving. I mean, this is a very small space here, right? It's the difference between, so probably 1.41 is right there. What's the next move? How do I get a little closer?
Yeah, 2 at the end.
I tack on the 2. Cool. Camila, how do I get one more step closer?
We're gonna add the 1 again.
Tack on the, or the, oh,
Oh, yeah.
oh wait, we actually, we went that, right? We've skipped our 4 there. Do you see what I mean? Just grabbing the next digit. So, now I'm gonna go to 1 point, then the next, just keep going. So just keep grabbing more and more decimals. Each one of those is a rational number, and each one is getting closer. But like you said, I can't get there. To get there, I have to allow all the digits in this expansion. And once I do that, that is irrational. And the full number itself is not in here. It's not in here. So this end that's on here, we can't get to. The max does not exist. Is this making some sense? Because if you're getting this, you're starting to see the problems that real analysis was built to fix, to deal with. Any questions? Let me know. I'm happy to explain this again. Good. And 0's cool because 0's already in irrational, right? So that's all good. But if I put square root of 2 minus 1 in there, instant trouble. No max, no min. Okay. Let's get a couple definitions out here. So an upper bound for a set is any number that's bigger than everything in the set. Let's just do a sequence of definitions, and then we play with the definition. Given a set S in the reals, and S is not empty because we just don't want to deal with weird non-empty stuff. Just makes things painful to think about. Got some subset of the reals. If M is, if X is less than or equal to M for all M, for all X in S, M is an upper bound. How does this differ from a maximum? Look at the definition. How is this differing? What's the difference between this and max? Go back to the definition. Think about a max. What was the definition of max? And there's a subtle thing that's missing here that makes this might not be a max. It could be a max, but it doesn't have to be. It's more, yeah, Cormac.
M is not included in.
Yeah, so this thing doesn't have to be in the set itself. So put a note, an upper bound is not necessarily in the set. So we'll come back to the set that we had, which was pi e 1 over pi 1 over e. We probably wrote it in a different order. We got the max was pi, the min was 1 over pi. give me an upper bound. So examples, blank is an upper bound. Give me a number that's bigger than all of these numbers. Give me one.
4.
4, I like it. 4 is an upper bound because all these numbers are less than or equal to 4. It's not the max. Recall, pi was the max. 4 is an upper bound. 5 is an upper bound. How many upper bounds are there? Infinitely many. There are infinitely many upper bounds. I'm just going to say UBs so I don't have to keep writing that. On your paper, write the definition of lower bound of a set S. So given a set S, again, write the definition for lower bound. You got something you like, Camila? Yeah, what would we say here?
M is less than or equal to X for all X's in the set.
Lovely. It's less than or equal to everything in the set. Could be a min, doesn't have to be a min. How many lower bounds are there? Infinitely many. Thank you. So we say a set is bounded above if there is an upper bound. We say it is bounded below if there is a lower bound. Christian, your brain's already there today. Can you give me an example of a set that is not bounded above? Not bounded above.
It would just be like anything with infinity.
Anything with infinity. Now we can toss infinity in. I just wanted to vindicate you with infinity. Yes. So, e.g., 1 to infinity is not bounded above. So these definitions where I said there's infinitely many upper bounds and infinitely many lower bounds, that there should be a caveat there, that only if the set is bounded to begin with. So when I say this, an upper bound is not necessarily in the set, or when I say there are infinitely many upper bounds, if there is at least one. And there are infinitely many lower bounds if there is at least one. As soon as you got one, you got a whole slew of them. Ms. Cecil, what is an example of a set with no lower bound and no upper bound? could work off of this guy here, right? We got one with, this has no upper bound. How would I tweak this so that it had no lower bound either? There we go, solid, awesome, thank you, perfect. And so this set here, the whole real line, which is just the whole real line, has no upper bound, no lower bound. Beautiful, thank you. Lovely, awesome, cool, all right. Complications, more complications. Probably never spent like 45 minutes just talking about bounded stuff in your whole mathematical career. Now it gets super interesting, and we can finally answer that square root of 2 issue. Definition. Make sure we get it right here. Suppose S is a subset of the reals, it's not empty, and is bounded above. So there's some place to, if I looked on the real number line, there's some place to the right of it where there's just space forevermore. And I know that once there's an upper bound, there's infinitely many upper bounds, right? So if I have a set, and the set looks like this, and whether or not it, you know, and maybe actually it skips and it's got like a thing like this, and then put an open thing there. So let's say S looks like this. It's this half open, half closed interval, and then this open interval, there's space in between. Here's an upper bound. That's what I'm saying. It's something that lives to the left of some number. Here's another upper bound. Here's an upper bound. Here's an upper bound. Now watch what I'm doing here as I get in there. Here's an upper bound. Here's an upper bound. And I'm kind of moving toward the set. At some point, I'm going to get to an upper bound that spills into the set. Right? If I keep moving, if I keep dropping my upper bounds, eventually, like if I don't want to go too far because that's not an upper bound. There's stuff in the set that's above it. So what we want to think about now is what's called the least upper bound. That's where I'm headed with this. And so this is the idea of limits kind of coming in there. I'm approaching from the right. So Cormac, and this will help with that idea of that whole square root of 2, or that 2 thing. And it'll also help us get, we don't need infinity. -1 over infinity, we got it. So the definition we're headed toward is least upper bound, but we have a much fancier word than this. We say capital M is the supremum. Latin fans, gotta be loving this shit. Is the supremum of the set S. And we write it like this, M equals, and you will actually start saying it, soup. I'll talk about the soup of something. Soup of S. And I mean the supremum. And another, sometimes you'll also see this. We won't use this because it doesn't sound as cool. It is the least upper bound. The lub of S. Doesn't that, I don't know. Supremum. The supremum, not the lub. They're the same thing. Least upper bound. Supremum. Beautiful. If, first off, there's 2 conditions. M is an upper bound. And we're going to use the definition that's in our book for the second condition, but there's other ways to write it. And we might explore that. But we're just going to work with this one today. If I've got another number, m prime, and it's less than that upper bound. So, picture time again. Let's make this fancy. Let's make this less fancy over here. Here's my set S. Oh hell, I'll tack on a few things like that. So far, if this is S right here, this half open interval, little dot added on to the left side, here I've got an M that's an upper bound. But I'm talking about M being the supremum, so I'm gonna put M right here. It's gonna turn out that that location right there where the hole is the supremum. It's as close as I can get to that thing without falling into it. So this M here is going to equal the sup of that set S. And you'll see in the second condition, if it's the sup because it's an upper bound, everything's to the left of it, and if I fall to the left of it, if I pick some number that's less than that number, then there is some element of S that is to the right of M prime, such that X is bigger, and let's write it like this, M prime is less than that X. And now we have a supremum. Let's think about that before we talk about its companion. You know, I was really happy for the break, but I kind of wish we had another day this week. We'll make it somehow. We'll be okay. But I don't know, I'm just getting super jacked about this. So let's take a look at a set. Examples. S is, let's go back to now. Oh hell, no, make it sorry. Just even simpler. Sorry. Come back. We'll go back to that infinity minus 1 over infinity thing and knock that shit out. So this set S is bounded. Let's write everything we know about it above. It is bounded below. It has a minimum, 1. It doesn't have a maximum because that open end. It's not 2, it's not 1.9, it's not 1.999, but it has a supremum. So first off, check out what I know. It's bounded above, awesome. So it's bounded above. I need to find the least upper bound. So the supremum of S, and you kind of just, you can feel this out. What is the supremum of S? What is the least, closest I can get from the right without falling in?
2.
Yes, 2. Awesome. Is this, how's the, your Cormac question? Yes.
The M prime is less than X. Can M prime be equal to X?
It could be, yes. Well, wait, hold on, let me think. Thinking I'll see. Let me pick out a small example. Let's say there's this like 2 little dudes in there. And so S is just these 2 points. And here is the supremum. So sometimes the sup can be in the set. You can get there. This is the supremum because this is an upper bound and it is literally the least upper bound. Everybody is less than or equal to it. So let's pick another M. Well, I don't need to, yeah, this will still work out okay. So let's say I did like M prime was here. Then this can still be the X that's to the right of it. I think we need to keep strict inequality because what we're really hoping to get, and I'm going to give you another characterization in a minute, but we want this softness as we move to the left. That's such a good question.
Cause x is included in s,
Right.
so if m prime were equal to x, it would still be included in s. And would be a
So let's see here. Well, I think the only way that could, no, I don't think so. So tell me your reasoning again. I actually think we have to have strict inequality. Give me your example that you're thinking of. Yeah, give me an example.
I don't know if I could think of an example. I was just thinking because x is included in s,
Yes.
so then if your m prime is less than x, wouldn't you still have an x greater than your supremum then?
Wouldn't m prime and m have to equal each other then?
Yeah, I think, let's see. So, only thing I can think of is there's 2 points in it. There's 1 point. I think, let's try that. There's this 1 point. There's the soup, right there. There's nowhere else to go. If I move a little to the right of it, it's not the least upper bound. If I pick any place left of here,
I actually think I had the definition mixed up.
I think so too.
Yeah, I was thinking m prime was the supremum.
Okay. Yeah, and I think that's what, and Liv was like, yeah, they had, yeah. So I think that, you feel better?
Yeah.
Okay, cool, awesome. That's great. These are the discussions that are gonna make it good. Let's talk about the flip side. So, again, I'm gonna say that, so definition, S is a real number subset. It's a collection of the real numbers. It is not empty. And this time I'm gonna say it's bounded below. And what we want to define now is the counter to the soup. It's called the infimum. We say, and let's see, did I use capital M over there? Yeah, so let's use little baby m. M is the infimum of S, and we write little m equals inf S. Give me the 2 counters about little m. So think through, what are the 2 conditions that make us a least upper bound? So again, we're trying to get as close from the left as possible. How do we get as close to the left as possible without spilling into the set? Might possibly spilling into the set, but as close to the left, from the left as possible. I have to start bringing my own. Buy an outhouse and just set it out back and we can use it. Ridiculous. Anybody feeling like they've got some resolution on this? Feeling like it, Carmick? Camilla, you feeling? Still feeling a little, yeah. Liv, you got something starting to manifest? Still?
Still thinking.
Okay. See, you got something going there? Okay, it's all good, it's all good, it's tough. Christian, are you starting to hone in on something?
I think so.
Maybe you guys can help me out. Cormac, what do you think the first condition is?
N is a lower bound.
Gotta be a lower, it's gotta be to the left. So if we're trying to get the closest from the left as we can, we need to start on the left. So absolutely, so little m is a lower bound of S. Awesome. Christian.
For the second one, I said if m prime is greater than m, then
Yeah.
there is some x that is an element of s such that m prime is less than x.
There we go. So if I move, if I'm truly at the closest I can get, and that's little m, if I fall to the right, there's something in the set inside there. And it might be this first thing, potentially. There could be a big old space there. But yeah, exactly, very well done. So if I move a little to the right, m prime, then there is some element of the set that is less than my new lower bound, my new mark, which isn't a lower bound at all. It's just some mark in the set, or to the right of the leftist most part of the set. Sorry, I'll shut up if that just starts getting confusing. That is the infimum. So from here, we're gonna play. Can I answer is there anything I can clarify before we start to play? So I'm gonna give you a bunch of sets. I'm gonna ask for the inf and the sup. This is that first problem that I put up here for the homework for next week. It had all the subparts. That's what it is. It's find the inf and the sup of all these different sets. So let's do that together. Let's at least warm up. We got lots of time to warm up. For next Monday, you will be doing yourself a huge favor if you read the section on the completeness axiom in the book. And it's just in this section 4. And then so read that, and the denseness, because I don't think we're gonna get there. I did spell it right. Denseness of the rationals in the reals. Give that a scan, give your brain a chance, plant some seeds. Whether or not those seeds sprout before next Monday, that's okay. You're gonna lay some neural pathways for this stuff. All right, so practice. Sups and infs. Real analysis begins today. Find supremum and infimum. I don't know why I write these backwards, because infimum is generally to the left of S. Allow me to say each set so I don't have to be pedantic and write S equals every freaking time. Each set, A. All right. So first one is 2 to 7, the closed interval. B is the open interval 2 to 7. Wow, okay, but then I wrote the same thing, so that's not cool. There we go, open interval 2 to 7. What is the supremum of the natural numbers, and what is the infimum? How about the rationals? And how about a set of rationals that are between square root of 2 and square root of 3? There's like a really, I'm gonna put it down, but I don't know, we'll get there, but you can definitely enjoy this. This will be good. I just like the way this set looks. I honestly have no idea what it is yet. I haven't thought about it, but it looks cool. Let's take a minute. Maybe the bathroom's finally open.
You.
Sorry.
So this would have a minimum or maximum.
That's right, yes, good, good.
Does it have a minimum or maximum? Like if it doesn't have a maximum, it can't be upper bounded or it can't?
So does this have an, let's start with just upper bound. Is there an upper bound to that set? Just one? Is there some number that's bigger than all those? And we're thinking this set itself is just the rationals, but we think when we find soups and imps, we're thinking we got all the numbers at our disposal.
So yes.
There is. What is the smallest real number? Now you know that that's not irrational. And that's why you're saying it's not in the set. But how close can I get if I'm coming this way? Is square root of 3 an upper bound on that set? So why you ask that? Tell me why you think that's it can be, but what's your question stemming from?
Because square root 3 is not a rational number.
That's right. So square root of 3 is not in that set, but for soups and imps, we get everybody.
Okay.
Your soup can be irrational, and I think that's what's sticking you. Yeah.
Okay, yeah, that makes sense.
Yeah. Does that make sense?
Yes.
So what is the soup?
Square root 3.
What's the imp?
Square root 2.
It's gone.
Good. For that one,
Mhm.
like, is there even?
Well, so let's think. So is there an upper bound?
Yeah.
What? Give me an upper bound. Give me a smaller one.
7.00001.
Give me an even smaller one.
Let's go.
So an upper bound, I think you're thinking an upper bound has to be bigger than everything in the set, but an upper bound is greater than or equal to everything in the set. I think that's what's snagging you. And then it just becomes easy.
Yeah.
There you go. Yes. Perfect.
Okay.
Perfect. Yeah. You do it on this one here? Yeah. So this one here. So what do you think? Can I see the others?
Yeah, I was just going to say.
Oh, you're doing
I
soups
think
first.
yeah,
Okay, got
yeah.
it. Yeah, that's great.
Getting your stuff with the maximum.
Okay. Yeah. So you did great. So that is the soup there, because 7 is above. It's to the right. Think to the right. You might want to draw a picture to help yourself. Think of the number line, and there's everything from 2 on up to 7. So I've got a little line segment. How close can I get from the right? And so what's an upper bound is 7 here, and it's also the smallest I can get, because if I said my upper bound, my least upper bound was 6.9, actually, can you draw a number line for me right there? Yeah, let's do it so we have a picture. And now put a little dot that's 2, and a dot that's 7, and then kind of make everything heavy in between there. You know, color it in just a little, make it thicker between 2 and 7. Yeah, just between 2 and 7. Yes, man, perfect. And let's make that extend out just a little, not the heavy. Yeah, perfect. So, can I see your pencil? Yeah. So, an upper bound. 8 is an upper bound. Yeah. So there's 8. 7.5 is an upper bound. The smallest upper bound that I can get, and an upper bound can be in the set itself, is 7. If I fall a little bit to the left of that, there's stuff in the set that's to the right of that. So my least upper bound is 7 here, because anything less has stuff bigger than it. Does that make sense? So let's think infimum. Now infimum is the other. So give me a lower bound. Oh, I like it. Okay, there we go. Now we're getting crazy. And so I could do 1.99. What's the greatest lower bound I could pick? 2, because 2 is actually in that set. So the greatest lower bound, the infimum, is 2, because if I pick a one that's bigger than that, it can't be anything that's greater than that is going to have stuff to the set from the set and to the left of it. So and you might want to think in your head, least upper bound, greatest lower bound, until you get used to those words. And I think Does that make more sense when you say, yeah, so think of it that way. So how about here, let's do that one together. What's an upper bound on that set? Let's do the picture. Okay. So what's an upper bound? 7.1. Give me another one that's smaller. Okay, cool. So is 7 an upper bound on all this stuff? It is. But if I go a little bit less, if I go to like 6.9, 6.99's in that set. So the least upper bound is 7. What's the greatest lower bound? There you go. Do you see how? There you go. Does that make more sense? Awesome. Fantastic. How we doing? Okay. Oh, yeah.
I'm not sure if any of these
They are. They're all okay. They're great.
and I don't have this.
Yeah, this is great. Oh, which one? There is none, because it's not bounded above.
Okay.
So you have to be, okay, let's go through this real quick. Sorry, I would have come take a look at what you're doing, but ran out of time. Let's go through these. Soup is 2. Infimum, so soup is 7, infimum is 2. Yeah? Soup 2, soup 7, Lord. Soup 7, infimum 2. Inf, what's the inf?
0.
1. Because 0's not in the set.
You're right.
Some people define it that way. So if you're doing it that way, Liv, then like 0 would be in there. But the way we did the natural started at 1. So here the infimum is 1. There is no soup because this set is not bounded above. So that's a tricky one. What about here? Inf.
Doesn't exist.
No lower bound. What about soup?
Doesn't exist.
Doesn't exist. So D on EM, both those. No soup, no inf. Inf. Root 2. Is that making sense, everybody? Inf. Soup.
Root 3.
Root 3. The soup and the inf can be irrational. These things can be any real number. This set's the trick. This set is only in the rationals, but its soup and inf live in the irrationals. And then this one, I haven't really, maybe think about it over the weekend. We'll pick it up. I'll take it. If you want me to look at what you got, I honestly don't know, but I would write out this set, so like when n equals 1, it's 1. When n equals 2, it's 2.
3 is 1/3.
And 3 is 1/3. When n equals 3, it's 1/3. So yeah, take a look. That set's pretty weird. I think the inf is 0.
It would be, I think 1, unless you define like n as having 0 within it. Right?
Yeah, so n won't have 0 in it. But so why did you say that? What did you say?
Because isn't the lowest you can go 1 because all like the
But I think you're gonna have all the odds in there.
oh wait, yeah, you're right.
You know what I'm saying? So you're like getting closer to 0, but you're never hitting 0. And then I think you do not have a soup because all those are gonna be, yeah. Cool. Awesome. Fun, friends. All right, cool. We got stuff. You got stuff due on Friday. Please get that to me by 1, and I'll see you on Monday. And I'm available. Email me if you need to chat about anything. Thank you. Oh, or now. Oh, yeah. Would you mind hitting stop on that, please? Thank you.